Radiocarbon dating is a method for determining the age of an object containing organic material by using the properties of radiocarbon, a radioactive isotope of carbon. The method was developed by Willard Libby in the late 1940s and soon became a standard tool for archaeologists. Libby received the Nobel Prize for his work in 1960. The radiocarbon dating method is based on the fact that radiocarbon is constantly being created in the atmosphere by the interaction of cosmic rays with atmospheric nitrogen. The resulting radiocarbon combines with atmospheric oxygen to form radioactive carbon dioxide, which is incorporated into plants by photosynthesis. Animals then acquire 14C by eating the plants. When the plant dies, it stops exchanging carbon with its environment, and from that point onwards the amount of 14C it contains begins to decrease as the 14C undergoes radioactive decay. Measuring the amount of 14C in a sample from a dead plant or animal such as a piece of wood or a fragment of bone provides information that can be used to calculate when the animal or plant died. The older a sample is, the less 14C there is to be detected, and because the half-life of 14C is about 5,730 years, the oldest dates that can be reliably measured by radiocarbon dating are around 50,000 years ago, although special preparation methods occasionally permit dating of older samples. The idea behind radiocarbon dating is straightforward, but years of work were required to develop the technique to the point where accurate dates could be obtained. Research has been ongoing since the 1960s to determine what the proportion of 14C in the atmosphere has been over the past 50,000 years. The resulting data, in the form of a calibration curve, is now used to convert a given measurement of radiocarbon in a sample into an estimate of the sample's calendar age. Other corrections must be made to account for the proportion of 14C in different types of organisms, and the varying levels of 14C throughout the biosphere. Additional complications come from the burning of fossil fuels such as coal and oil, and from the above-ground nuclear tests done in the 1950s and 1960s, because the time it takes to convert biological materials to fossil fuels is substantially longer than the time it takes for its 14C to decay below detectable levels. They contain almost number 14C, and as a result there was a noticeable drop in the proportion of 14C in the atmosphere beginning in the late 19th century. Conversely, nuclear testing increased the amount of 14C in the atmosphere, which attained a maximum in 1963 of almost twice what it had been before the testing began. Measurement of radiocarbon was originally done by beta counting devices, which counted the amount of beta radiation emitted by decaying 14C atoms in a sample. More recently, accelerator mass spectrometry has become the method of choice. It counts all the 14C atoms in the sample and not just the few that happen to decay. During the measurements, it can therefore be used with much smaller samples, and gives results much more quickly. The development of radiocarbon dating has had a profound impact on archaeology. In addition to permitting more accurate dating within archaeological sites than previous methods, it allows comparison of dates of events across great distances. Histories of archaeology often refer to its impact as the radiocarbon revolution. Radiocarbon dating has allowed key transitions in prehistory to be dated, such as the end of the last ice age, and the beginning of the Neolithic and Bronze Age in different regions. Samples for dating need to be converted into a form suitable for measuring the 14C content. This can mean conversion to gaseous liquid, or solid form, depending on the measurement technique to be used. Before this can be done, the sample must be treated to remove any contamination and any unwanted constituents. This includes removing visible contaminants, such as rootlets that may have penetrated the sample since its burial. Alkali and acid washes can be used to remove humic acid and carbonate contamination, but care has to be taken to avoid destroying or damaging the sample. Material considerations: it is common to reduce a wood sample to just the cellulose component before testing, but since this can reduce the volume of the sample to 20% of its original size, testing of the whole wood is often performed as well. Charcoal is often tested but is likely to need treatment to remove contaminants. Unburnt bone can be tested. It is usual to date it using collagen, the protein fraction that remains after washing away the bone's structural material. Hydroxyproline, one of the constituent amino acids in bone, was once thought to be a reliable indicator as it was not known to occur except in bone, but it has since been detected in groundwater. For burnt bone, testability depends on the conditions under which the bone was burnt. If the bone was heated under reducing conditions, it may have been carbonized. In this case, the sample is often usable. Shells from both marine and land organisms consist almost entirely of calcium carbonate, either as aragonite or as calcite, or some mixture of the two. Calcium carbonate is very susceptible to dissolving and recrystallizing. The recrystallized material will contain carbon from the sample's environment, which may be of geological origin. If testing recrystallized shell is unavoidable, it is sometimes possible to identify the original shell material from a sequence of tests. It is also possible to test conchiolin, an organic protein found in shell, but it constitutes only 1 to 2% of shell material. The three major components of beta-humic acid, humins, and fulvic acid. Of these, humins give the most reliable data as they are insoluble in alkali and less likely to contain contaminants from the sample's environment. A particular difficulty with dried peat is the removal of rootlets, which are likely to be hard to distinguish from the sample material. Soil contains organic material, but because of the likelihood of contamination by humic acid of more recent origin, it is very difficult to get satisfactory radiocarbon dates. It is preferable to sieve the soil for fragments of organic origin, and date the fragments with methods that are tolerant of small sample sizes. Other materials that have been successfully dated include ivory, paper, textiles, individual seeds and grains, straw from within mud bricks, and charred food remains found in pottery. Preparation and size. Particularly for older samples, it may be useful to enrich the amount of 14C in the sample before testing. This can be done with a thermal diffusion column. The process takes about a month and requires a sample about 10 times as large as would be needed otherwise, but it allows more precise measurement of the 14C-12C ratio in old material and extends the maximum age that can be reliably reported. Once contamination has been removed, samples must be converted to a form suitable for the measuring technology to be used. Where gas is required, CO2 is widely used. For samples to be used in liquid scintillation counters, the carbon must be in liquid form. The sample is typically converted to benzene. For accelerator mass spectrometry, solid graphite targets are the most common, although iron carbide and gaseous CO2 can also be used. The quantity of material needed for testing depends on the sample type and the technology being used. There are two types of testing technology: detectors that record radioactivity, known as beta counters, and accelerator mass spectrometers. For beta counters, a sample weighing at least 10 grams is typically required. Accelerator mass spectrometry is much more sensitive, and samples as small as 0.5 milligrams can be used. Use in archaeology. Interpretation. A key concept in interpreting radiocarbon dates is Archaeological Association. What is the true relationship between two or more objects at an archaeological site? It frequently happens that a sample for radiocarbon dating can be taken directly from the object of interest, but there are also many cases where this is not possible. Metal grave goods, for example, cannot be radiocarbon dated, but they may be found in a grave with a coffin, charcoal, or other material which can be assumed to have been deposited at the same time. In these cases, a date for the coffin or charcoal is indicative of the date of deposition of the grave goods, because of the direct functional relationship between the two. There are also cases where there is no functional relationship, but the association is reasonably strong. For example, a layer of charcoal in a rubbish pit provides a date which has a relationship to the rubbish pit. Contamination is of particular concern when dating very old material obtained from archaeological excavations, and great care is needed in the specimen selection and preparation. In 2014, Tom Hyam and co-workers suggested that many of the dates published for Neanderthal artifacts are too recent because of contamination by young carbon. As a tree grows, only the outermost tree ring exchanges carbon with its environment. So the age measured for a wood sample depends on where the sample is taken from. This means that radiocarbon dates on wood samples can be older than the date at which the tree was felled. In addition, if a piece of wood is used for multiple purposes, there may be a significant delay between the felling of the tree and the final use in the context in which it is found. This is often referred to as the old wood problem. One example is the Bronze Age trackway at Withy Bedcopse, in England. The trackway was built from wood that had clearly been worked for other purposes before being reused in the trackway. Another example is driftwood, which may be used as construction material. It is not always possible to recognize reuse. Other materials can present the same problem. For example, bitumen is known to have been used by some Neolithic communities to waterproof baskets. The bitumen's radiocarbon age will be greater than is measurable by the laboratory, regardless of the actual age of the context, so testing the basket material will give a misleading age if care is not taken. A separate issue related to reuse is that of lengthy use or delayed deposition. For example, a wooden object that remains in use for a lengthy period will have an apparent age greater than the actual age of the context in which it is deposited. Notable applications: Pleistocene, Holocene boundary in Two Creeks fossil forest. The Pleistocene is a geological epoch that began about 2.6 million years ago. The Holocene, the current geological epoch, begins about 11,700 years ago, when the Pleistocene ends. Establishing the date of this boundary minus which is defined by sharp climatic warming minus as accurately as possible has been a goal of geologists for much of the 20th century. At Two Creeks, in Wisconsin, a fossil forest was discovered, and subsequent research determined that the destruction of the forest was caused by the Valdez ice re-advance, the last southward movement of ice before the end of the Pleistocene in that area. Before the advent of radiocarbon dating, the fossilized trees had been dated by correlating sequences of annually deposited layers of sediment at Two Creeks with sequences in Scandinavia. This led to estimates that the trees were between 24,000 and 19,000 50,000 years old, and hence this was taken to be the date of the last advance of the Wisconsin glaciation before its final retreat marked the end of the Pleistocene. In North America, in 1952 Libby published radiocarbon dates for several samples from the Two Creeks site and two similar sites nearby. The dates were averaged to 11,404 BP with a standard error of 350 years. This result was uncalibrated, as the need for calibration of radiocarbon ages was not yet understood. Further results over the next decade supported an average date of 11,350 BP, with the results thought to be most accurate averaging 11,600 BP. There was initial resistance to these results on the part of Ernst Antefs, the paleobotanist who had worked on the Scandinavian Varv series, but his objections were eventually discounted by other geologists. In the 1990s, samples were tested with AMS, yielding dates ranging from 11,640 BP to 11,800 BP, both with a standard error of 160 years. Subsequently, a sample from the fossil forest was used in an interlaboratory test, with results provided by over 70 laboratories. These tests produced a median age of 11,788 plus or minus 8 BP, which when calibrated gives a date range of 13,730 to 13,550 cal BP. The Two Creeks radiocarbon dates are now regarded as a key result in developing the modern understanding of North American glaciation at the end of the Pleistocene. Dead Sea Scrolls. In 1947, scrolls were discovered in caves near the Dead Sea that proved to contain writing in Hebrew and Aramaic, most of which are thought to have been produced by the Essenes, a small Jewish sect. These scrolls are of great significance in the study of biblical texts because many of them contain the earliest known version of books of the Hebrew Bible. A sample of the linen wrapping from one of these scrolls, the Great Isaiah Scroll, was included in a 1955 analysis by Libby, with an estimated age of 1,917 plus or minus 200 years. Based on an analysis of the writing style, paleographic estimates were made of the age of 21 of the scrolls, and samples from most of these, along with other scrolls which had not been paleographically dated, were tested by two AMS laboratories in the 1990s. The results ranged in age from the early 4th century BC to the mid-4th century AD. In many cases, the scrolls were determined to be older than the paleographically determined age. The Isaiah scroll was included in the testing and was found to have two possible date ranges at a 2 sigma confidence level. Because of the shape of the calibration curve at that point, there is a 15% chance that it dates from 355-295 BC and an 84% chance that it dates from 210-45 BC. Subsequently, these dates were criticized on the grounds that before the scrolls were tested, they had been treated with modern castor oil in order to make the writing easier to read. It was argued that failure to remove the castor oil sufficiently would have caused the dates to be too young. Multiple papers have been published both supporting and opposing the criticism. Impact. Soon after the publication of Libby's 1949 paper in Science, universities around the world began establishing radiocarbon dating laboratories, and by the end of the 1950s there were more than 20 active 14C research laboratories. It quickly became apparent that the principles of radiocarbon dating were valid, despite certain discrepancies, the causes of which then remained unknown. The development of radiocarbon dating has had a profound impact on archaeology, often described as the radiocarbon revolution. In the words of anthropologist R.E. Taylor, 14C data made a world prehistory possible by contributing a time scale that transcends local, regional and continental boundaries. It provides more accurate dating with insights than previous methods, which usually derived either from stratigraphy or from typologies. It also allows comparison and synchronization of events across great distances. The advent of radiocarbon dating may even have led to better field methods in archaeology, since better data recording leads to firmer association of objects with the samples to be tested. These improved field methods were sometimes motivated by attempts to prove that a 14C date was incorrect. Taylor also suggests that the availability of definite date information freed archaeologists from the need to focus so much of their energy on determining the dates of the finds, and led to an expansion of the questions archaeologists were willing to research. For example, from the 1970s, questions about the evolution of human behavior were much more frequently seen in archaeology. The dating framework provided by radiocarbon led to a change in the prevailing view of how innovations spread through prehistoric Europe. Researchers had previously thought that many ideas spread by diffusion through the continent, or by invasions of peoples bringing new cultural ideas with them. As radiocarbon dates began to prove these ideas wrong in many instances, it became apparent that these innovations must sometimes have arisen locally. This has been described as a second radiocarbon revolution, and with regard to British prehistory, archaeologist Richard Atkinson has characterized the impact of radiocarbon dating as radical therapy for the progressive disease of invasionism. More broadly, the success of radiocarbon dating stimulated interest in analytical and statistical approaches to archaeological data. Taylor has also described the impact of AMS and the ability to obtain accurate measurements from very small samples as ushering in a third radiocarbon revolution. Occasionally, radiocarbon dating techniques date an object of popular interest. For example, the Shroud of Turin, a piece of linen cloth thought by some to bear an image of Jesus Christ after his crucifixion. 3 separate laboratories dated samples of linen from the shroud in 1988. The results pointed to 14th century origins, raising doubts about the shroud's authenticity as an alleged 1st century relic. Researchers have studied other radioactive isotopes created by cosmic rays to determine if they could also be used to assist in dating objects of archaeological interest. Such isotopes include 3He, 10B, 21Ni, 26Al, and 36Cl. With the development of AMS in the 1980s, it became possible to measure these isotopes precisely enough for them to be the basis of useful dating techniques, which have been primarily applied to dating rocks. Naturally occurring radioactive isotopes can also form the basis of dating methods, as with potassium-argon dating, argon-argon dating, and uranium series dating. Other dating techniques of interest to archaeologists include thermoluminescence, optically stimulated luminescence, electron spin resonance, and fission track dating, as well as techniques that depend on annual bands layers, such as dendrochronology, tephrochronology, and valve chronology.